Morning everyone. First of all, thank you for the jury members to be here for attending my PhD thesis talk. Thanks also to my directors and my colleagues and my friends and family who are here to support me and assist this PhD talk. So I'll be presenting my PhD regarding positioning and mapping for aided robots using onboard perception for autonomous missions. So as you can see, this is an aided robot. You probably know these aided robots. They are also called as drones. So in the recent years, they have increased a lot in demand due to the numerous applications that these aided robots can solve. So over here, this aided robot has an autopilot inside, which you cannot see probably, which can enable the manual flight using a radio transmitter. When we put some onboard sensors, like a camera in this case, as well as an onboard computer, we can give this aided robot the capabilities to fly autonomously and perform several missions for us. So first of all, let's look into some of the cool indoor applications that these aided robots, these autonomous aided robots, are capable of solving today. So applications like airplane inspections, this was performed by our group. I participated in this project. Then inspections such as thermal power plant inspections, which was also performed by our group. I participated in it as well. Then inspections like chimney inspections, then underground mine inspections. This was performed by the University of Nevada. Penstock inspection, tunnel-shaped penstocks, which was inspected by the University of UPenn, and like applications like inventory management. So every year, also the research community gives us or provides several real-life oriented challenges for these autonomous aided robots. One such competition is the International Micro-Aided Vehicles competition. This year it was held in our school, organized by our group, where the challenges were inventory management as well as package delivery. So let's look into a general structure of how an autonomous aided robot looks like. So over here you have an aided robot which is mounted with several sensors. These sensors provide sensor measurements which go into the localization and mapping module. This module generates the robot state and the environment. So using this data, the high-level planner, along with the mission points provided by the high-level mission planner, is able to plan the obstacle-free path for the aided robot. This obstacle-free path then goes into a high-level control module, which can be a position or velocity control, and which generates an attitude and thrust commands for the low-level control, which is responsible for controlling the motor speeds of the aided robot. So during this thesis, I focused mainly on the localization and mapping module, because I think this is one of the most critical modules inside an aided robot, as failures or inaccuracies in this module can cause inaccuracies and failures in all the connected components. So let's see how these failures can cause catastrophes like this on board the aided robots. So failures in sensor measurements or perception can cause these errors. This was again an error of perception where not perceived properly. Over here as well. Over here there was an error in the sensor. Over here the perception did not work properly. Over here as well. Also, the research, there are several researches being performed during these years, where there are autonomous aided robots doing very complex maneuvers like building a rope bridge, completely autonomous. But there is a trick over here. As you can see, they use these motion capture systems which are mounted external, and these aided robots do not have any onboard perception. So these are responsible for providing accurate pose estimates for this aided robot. Thus, one focus of this thesis is also using onboard perception, because these cameras are not, it's not possible to take this system to a real-life application. So let's see the main contributions of this thesis and how I've outlined this presentation today. First is my first contribution is in the localization and mapping part, and the second is in the autonomous missions. In the localization and mapping, my first contribution is in pose estimation, where I'll first explain the flight altitude estimation using conventional sensors. So the flight altitude estimator is capable of estimating the correct flight altitude of the aided robot in cluttered and unstructured environments such as these. Then the section 2 of pose estimation is the pose estimation using semantic stereo-visual odometry, where I combine the low-level features in the environment like textures along with high-level semantic objects such as chairs, in order to estimate the drift-free pose of the aerial robot. Then is the part 2 of localization and mapping, where I present the pose and map estimation, where the section 1 consists of the altitude estimation and planar mapping using point cloud sensors. This enables the aerial robot to map the horizontal planar surfaces as well as estimate the true flight altitude in dynamic as well as static environments. And the section 2 of pose and map estimation is pose and map estimation using visual semantic SLAM, where I present a complete SLAM framework which is capable of creating a sparse semantic map of the environment, simultaneously estimating the pose of the aerial robot. Then in the autonomous missions, I would like to present the first contribution, which is in the International Micro-Aerial Vehicles competition, where the aerial robot has to interact with several diverse components in the environment, such as the bucket, where it has to release the item inside the bucket. The section 2 would be autonomous thermal power plant inspection, where the aerial robot autonomously inspects a real thermal power plant. And the last section is the autonomous airplane inspection, where the aerial robot inspects the airplane completely autonomous. So let's come to the part of pose estimation, the section 1, which is the flight altitude estimation using conventional sensors. So consider a simplified environment where you have an aerial robot which needs to move from point A to point B, maintaining this altitude reference. So if it uses distance sensors for measuring the measurements from the distance sensor, when it moves over the objects, as it measures with respect to the objects below it, in this case the aerial robot will go up and then come down to this point B, causing a irregular flight. Whereas in the same case, if it uses accelerometers or barometers for estimating the altitude, if the aerial robot has to move the same point, it can, instead of reaching the point accurately, it will have some errors. So several state-of-the-art algorithms exist, such as the one over here, where the authors present a completely autonomous solution and provide the altitude estimation using a laser sensor, but they do a very heuristic approach in order to estimate the flight altitude and do not do the flights in presence of ground obstacles, which are common in an indoor environment. As well as this paper also, the authors present a circular laser and camera-based altitude estimation technique, but do not assume any ground obstacles present. So thus, we present a fast, robust, and lightweight extended Kalman filter-based flight altitude estimator, which we make it open source for the research community. So it has the following features. Firstly, it's modular in design, so the user can integrate several altitude measuring sensors depending on the requirements. So it can be 3 distance sensors or 1 distance sensor, 1 barometer and accelerometer, depending on the requirement. Then it has the capability of auto calibration of the sensors, so it can estimate the bias in the measurements of the sensors. It has the capability of synchronous prediction stage, where the estimation is executed whenever it is required by the control algorithm, and an asynchronous update stage where the state is updated whenever the measurements arrive. So this is how the general structure of the filter looks like, where the first stage is the aerial robot, consisting of its altitude, which is along the z-axis, the velocity and the acceleration also about the z-axis, then the angles, the theta and the roll and pitch angles, as well as the angular velocities about the x and y axis. In this case, there is also a state of the ground obstacle, which enables the aerial robot to estimate its true flight altitude whenever it's flying over an object, as it estimates the altitude of the ground object below. Then it has an IMU sensor, where it incorporates the biases which can be present in the linear accelerations of the sensors, as well as the measurements that it incorporates are the linear accelerations about the z-axis, the roll and pitch angles, as well as the angular velocities about the x and y axis. In case of the barometer sensor, it incorporates the bias, and in the measurements, they are the measurements which are received by the pressure measurements. And the distance sensor only incorporates the measurements which are the measurements from the distance sensor with respect to the object below or the floor below. So we test our approach using our custom aerial robotic platform, which has a Pixar autopilot. The autopilot already has incorporated the IMU sensor and the barometer, as well as we mount an additional laser altimeter, the Lightware SF10A, used as the distance sensor in this case. So this is the experiment we performed, one of which is closing the altitude control loop of the aerial robot using the estimate from our approach, and it's able to fly in this unknown and cluttered environment with several ground obstacles. So as you can observe from this graph over here, the barometer presents bias in its measurements, whereas our approach, which is combining the information from all the sensors, is able to estimate the true flight altitude of the aerial robot. While zooming into this same graph, you can observe the laser measurements which are being effected while the aerial robot is flying on top of the objects, and our filter is able to estimate the ground altitude below it. We also add the capabilities, where in this experiment we add the capabilities for the aerial robot to, for the estimator to estimate if the aerial robot is flying from an elevated platform, and also if it has to land on a moving platform. So over here you can observe the aerial robot. The filter incorporates the initial state of the aerial robot, the initial height of the aerial robot, and the rest of the experiment is executed in the same environment, and the filter is able to maintain the true flight altitude of the aerial robot. So now we come to the section 2 of pose estimation, which is the pose estimation using semantic stereo visual odometry. So consider a simplified environment over here as well, where the aerial robot has to move from point A to point B, maintaining this line of reference. So if it uses, in this case, the low-level features for perception, which are the stars, there can be a point where it can lose the perception of this low-level feature, or there can be an error in matching these features because they look really similar. So what can happen is that the aerial robot can generate inaccuracies in the pose and can crash to the objects nearby. So several state-of-the-art algorithms exist. One of them is the SVO, the semi-direct visual odometry, as well as the other is the ROVIO, which is the robust visual inertial odometry. Both the approaches, as well as other visual odometry techniques, have the problems of error accumulation. So if the surface is shiny or the patterns are repetitive, they can accumulate errors in the pose estimates. Also, they have problems of complete divergence. So in this case, you can observe this is the yellow is the pose estimate by the VO, the visual odometry, and at this point, it will diverge away from the true pose estimate due to the low features present in the environment. So the basic idea behind the semantic stereo visual odometry is that in the same case where the aerial robot has to move from point A to point B, maintaining this line of reference, where it perceives the low-level feature, it will also perceive additionally a high-level semantic object, which is the chair in this case. So as it moves in the environment, if it loses the perception of the low-level features, or if it has errors in perceiving this low-level feature, it still has the perception of the high-level semantic object, which can enable it to reach the point B more accurately. But even semantic objects like chairs, which belong to the same class, have different shapes and size. So how do we use them exactly in order to improve this error in the pose estimates of the visual odometry? As you can observe, all these objects have one common planar surface, which is the horizontal planar surface. So we extract the horizontal planar surface from these semantic objects in order to improve the drift from the visual odometry. We thus present a real-time and robust particle filter-based approach, which we make it open source as well for the research community. It can it is modular in integrating the visual odometry algorithms. If the user requires a different visual odometry, it can be easily integrated in a plug-and-play manner. Then it loosely couples this visual odometry information with the IMU sensor data, and as well as the semantic horizontal planar information, which I explained in the previous slide. Thus, it's capable of estimating the complete 3D pose of the aerial robot. It consists of mainly two stages. So the first stage is the prediction stage, where we have our stereo visual odometry based on fast key point extraction, which estimates the pose of the aerial robot as it moves. But this is accurate for short time intervals, but a long time, due to low features in the environment or other errors, this can accumulate errors in its pose estimate. So thus we have the update stage, which updates the roll pitch angles of the visual odometry using the measurements from the IMU sensor, and in the semantic update stage, it updates the positions which are estimated, the position errors from the visual odometry algorithms. So over here you can see this is a semantic data received at a given time instant. SZ is the relative pose of the semantic data. SC is the class that it belongs to. Sn are the number of 3D points that can be present in that planar surface, and SP is the probability of the detection. So using this semantic data, we can map these data with an already pre-created map of the objects in order to improve the drift or error in the visual odometry pose. So we test our approach using the aided robotic platform, which is the Parrot Bebop tool, and we mount it with the Parrot Slam Dunk, which is a stereo vision sensor for performing the stereo visual odometry, and the Intel RealSense R200 camera performing the planar extraction set. So in this experiment, which we call it the ground truth evaluation, the aided robot is moved in an environment which has low texture, or I would say less texture in the environment, but also has a combination of high-level semantic objects. So in this case, when the aided robot is flown in a trajectory over performing several repetitive loops, we have an average trajectory error of 18 centimeters, whereas the visual odometry has an error of 85 centimeters. When comparing the average trajectory error to the OrtSlam tool, which uses low-level features for the mapping stage as well as the pose estimation, it has an error of 40 centimeters. So this is the video of the same experiment which I mentioned. Over here you can observe that this wall, as the aided robot goes near this wall, the visual odometry starts accumulating error in its pose estimate, whereas our approach, which is combining both the data, is able to maintain the drift-free pose, and thus the aided robot, which is closing its position control loop using the estimates from our algorithm, can navigate perfectly in the environment and can come back and land from the takeoff point. Then we also evaluated its performance over longer trajectories of around 56 meters, where the aided robot, and you can observe in this experiment, the aided robot, which uses our estimate, takes off and lands at the same point, whereas the visual odometry has an error of around 2 meters in its estimate. So with this we come to an end to the part of pose estimation, and let's start the part of pose and map estimation. And I'll start with the first section, which is the altitude estimation and planar mapping using point cloud sensors. So in the previous approach, which used distance sensors for estimating the flight altitude of the aided robot, these distance sensors, like the laser altimeters, perceive very little information about the environment at a given time instant. So over here you can observe in this graph, there are some complex, like when the aided robot flies over these objects, there can be peaks in the measurements as the laser altimeter doesn't perceive the object properly. So why not use a point cloud sensor, which provides us the same information but in a more richer manner? So we thus present a fast and robust Kalman filter-based SLAM approach using RGBD sensors. We also make it open source for the research community. It has the step of fast planar clustering segmentation and mapping using low resolution RGBD images. Thus it's able to estimate the flight altitude simultaneously mapping the planar surfaces at high frequencies of 50 to 54 Hz. We test the approach in both static as well as dynamic output. So over here, this is the part one. It's basically divided in two parts. Where this part one is the planar clustering and segmentation part, where first given a point cloud, we extract the normals from the point cloud, where these are the horizontal normals and these are the vertical normals. Using the orientation, we can segment the horizontal normals together and then segment out the 3D points corresponding to them. And thus, once we have the 3D points, we can compute the 3D centroids, the height centroids of these planar surfaces. So using this, we can go to the next step, which is the Kalman filter based for the mapping and the localization part. So it consists of the process model, which consists of a state with a single parameter of the altitude of the aided robot with some noise. The prediction stage follows a standard Kalman filter equation propagating the state as well as the covariance with time. And in case of the measurement model, it consists of the horizontal centroids, which we extracted from the previous step. And in the data association and update stage, we use the Mahalanobis distance in order to match the currently detected planar surfaces with the map of the landmarks, or these can be either mapped as new landmarks. So we first test our approach using the Kinect 2011 Kinect dataset, which has several complexity of the environment, different environments based on the complexity, and it depends on the number of obstacles present. And in this approach, the camera is moved from slow to fast speeds, and you can observe even with fast rotational and translation motions, which are really random of the camera, we have a root mean square error of around 12 centimeters in the altitude estimate. In the real flight, we then perform real flight experiments mounting a RealSense R200 camera on board the custom aided robotic platform and tested in both static as well as dynamic environments. So this is the experiment of the static environment, where the aided robot is, two experiments are performed at two different velocities of the aided robot, and these are the static objects present in the environment. And you can observe with these two speeds, even with these two different speeds of the aided robot, we have a root mean square error of 10 centimeters in the altitude estimate of the aided robot. We test then the approach in the same experiment, where the aided robot instead it is the same environment, but it has a combination of both static as well as dynamic objects. Even in this experiment with two different velocities, low and fast, the flight altitude estimate has a root mean square error of around 4 centimeters. So with this, we finish the section 1 and we come to the section 2, which is the pose and map estimation using visual semantic SLAM. So again, consider a simplified environment where the aided robot is unaware of the environment, and it has low-level features such as the stars and one high-level semantic object, which is the book in this case. So as the aided robot moves in the environment, it can perceive these stars in order to compute its pose. And when it comes to this point where it can perceive the high-level object, it can extract the planar surface and create a map with a label called book as well as its position. So as the aided robot moves in the environment, when it perceives these low-level features, it can accumulate error in its pose estimate, and the pose can diverge from the true pose. But at this step, when it comes back, it can detect this book, and the data association step can give a match with the already mapped features, and this can help correct the pose of the aided robot. So this is the basic idea behind visual semantic SLAM. There are several state-of-the-art techniques. One of them is OrSLAM 2, which is a complete SLAM framework which uses low-level features for creating a low-level map of the environment, simultaneously computing the pose of the camera. And there are techniques like SLAM++, which creates a high-level object map of the environment using chairs or tables, simultaneously computing the pose of the camera. But techniques like OrSLAM can have errors in the loop closure due to an environment being really similar or featureless. So in this example, you can see this environment really has similar features, and at this step, the loop closure is completely destroyed because the environment, because of the similarity of the features in the environment. And techniques like SLAM++ require really high computational resources, which is a limitation on board the aided robot, as well as require an accurate 3D model in order to map these objects. So we thus present a lightweight, fast and robust semantic SLAM framework, which we make it open source for the research community. It's modular in structure in the way of that it can integrate several visual odometry or visual inertial odometry pipelines depending on the application in hand. It can also integrate several object-based detectors as required, and if required, it can also easily integrate in other perception algorithms. In this case, we use a fast and efficient planar extraction technique from the detected semantic objects. Thus, our approach is generalizable to several objects, with several semantic objects which have planar surfaces. So this is the general overview of how the algorithm looks like, and I'll first explain the part A, which consists of the visual odometry or visual inertial odometry front end. So we test this part with several state-of-the-art techniques. First of all, the ROVIO, which is the robust visual inertial odometry, the Snapdragon visual inertial odometry, as well as the ARTA visual odometry, depending on the experiments and depending on the performance of each algorithm, the best performance of each algorithm given the environment. Then we have the planar extraction and data association step, where you can observe over here in the right, these are the object detectors, these are the detections which are received by the object detectors. Over here we use the tiny YOLO and a custom shape color object detector, which provides these detections, and we then can segment the point cloud corresponding to these object detection, then segmenting the planar surfaces inside. So the green are the inliers to the planar surfaces extracted. So given a semantic data that we received at a given time instant, and given a map which we are all creating simultaneously, the semantic data can be matched with the map in the following way. So first we check whether the class type is similar to the class type of the map landmark. Then we check whether whether the plane is horizontal or vertical. Then we check whether the normal orientation, the error in the normal orientation is below a given threshold. And then we check using the relative pose and the covariances, the Mahalanobis distance, in order to match this semantic data or to create a new semantic map. And the last step is the graph optimization backend, where we use the G2O open source library for the optimization. And over here you can see we create a graph using the odometry nodes, and the edges are the poses between the odometry nodes. Over here, these are the nodes of the semantic planar surfaces extracted, and the edges between the odometry nodes and the landmark nodes are the relative poses between them. So we test this approach using, firstly, in a standard data set where we test it on the Tomb benchmark experiment, and you can observe in this table, we tested on 4 sequences. And you can observe in this table, when we use the RTAP visual odometry as the front end in this case, our approach presents better results extracting the planar surfaces and mapping them. When you compare our approach to the state-of-the-art object-based SLAM techniques like mass fusion and fusion plus, the experiment we carry out is the long haul experiment, where the aided robot is moved in a handheld manner, as we couldn't fly over there, and it's creating the sparse semantic map of these recycled beams as it's moving in the environment. So over here you can observe in green are the estimates from the visual inertial odometry, which drift as it moves in the environment, whereas our approach, which is simultaneously mapping the planar surfaces, the high level planar surfaces of the semantic object, is able to correct this error. And this is the 3D map of the environment generated from the pose estimate from our approach. So over here in this experiment, this is the long corridor experiment, where we perform it in a long corridor with challenging illumination conditions. So due to these challenging illumination conditions, the visual inertial odometry has a huge drift in its estimate. Over here in the altitude, in the z-axis, it has an error of around 6 meters. Whereas our approach, which is using the semantic objects, in this case the chairs, is able to correct this error in the pose. Over here you can observe in the 3D map generated from the pose estimate, the blue are the errors in the visual inertial odometry. Then we also perform several experiments comparing the results to the ground truth data, where this is the first experiment in which we have an environment with several semantic objects, and the camera is moved in a repetitive manner. And when we come to this table over here, the visual inertial odometry, which we use as the front end, has an error of around 31 centimeters in its absolute trajectory, whereas our approach is able to correct this pose and improve this error in its pose. When we comparing it to the OrbSlam 2, which uses low-level features for the map creation as well as pose estimation, has an error of around 27 centimeters. We then perform the experiment in the same environment, but instead of moving the camera in a repetitive manner, we perform random motions in translation as well as rotations. So in this approach, we have an error of around 39 centimeters when comparing it to the visual inertial odometry, which drifts largely in its pose estimate. Over here, the OrbSlam 2 has better pose estimate, because the visual inertial odometry at one point drifts far away from its pose estimate. Our approach is though able to correct this pose estimate, but in this case it doesn't improve the pose estimate when comparing it to the OrbSlam. And then we perform the flights onboard the aerial robot, where it's moved at 2 meters per second, and our approach has an absolute trajectory error of 28 centimeters, whereas the VIO has an error of 65 centimeters. In this case, the ORFLAM 2 fails to provide any results because of the high angular motions of the camera, as well as the less amount of texture present in the environment. So thus it loses feature tracking, and it's not able to provide the pose estimate. So we finished the part of localization and mapping, and now I'll come to the contributions of autonomous missions. So before starting, I would like to just give you a brief introduction of the Aerostack framework, which we use in our group for the autonomous missions that we perform. So the Aerostack framework is a very intelligent and modular framework in terms of the algorithms that can integrate in for the autonomous missions, as well as the aerial robotic platforms. So during the whole length of my thesis, I worked on adding several aerial robotic platforms as well as onboard sensors in order to increase the capabilities of the Aerostack framework. Also, I have worked on the localization and mapping part, where all the previously presented approaches were integrated in this module, as well as other state-of-the-art localization and mapping modules in order, depending on the applications in hand. So after knowing a bit of Aerostack, let's start with the first challenge, which was the International Micro Aerial Vehicles Competition. So this was held in Beijing, China in 2016, and the competition was really challenging. Over here, the aerial robot had to take off from an operating zone in the moving platform. From a moving platform, it had to enter the house with unknown layout through either the door, window, or the chimney, pick up some items which were either red or blue in color, and release them in their corresponding buckets. So for this competition, we created a custom aerial robotic platform which was mounted with the Pixoc autopilot. Then we mounted it with several onboard sensors like the Hokuyo 2D laser sensor, Lightware SF10A laser altimeter for the altitude measurements, a bottom camera, and a RealSense R200 front camera. Then in this mission, we did not perform the picking maneuver, we performed the release task. So we took off the aerial robot with the items preloaded, and thus it had the release servos where the items were hanged. So in this case, we modified the Aerostack framework in order to be more capable to perform these intelligent missions. In this case, I worked on adding the aerial robotic platform as well as the onboard sensors to integrate it perfectly in the Aerostack framework. Then I worked on the localization and mapping part in the 2D SLAM, the altitude estimator, which was presented in the section 1 of the pose estimation, and the multi-sensor fusion state estimator, which was capable of estimating the complete 3D pose of the aerial. I dedicated a lot of time also on understanding the motion controller and tuning it properly so that this aerial robotic platform had a safe and stable flight while moving in the environment. It had other capabilities like the visual servo controller for the release maneuvers and the motion planner in order to compute the obstacle-free path. Then it had the high-level mission planner modules, which were responsible for planning the complete mission given the area, given the mission area. So we performed several simulation experiments, and then we perform also in a real-life replica in our lab, where this is the house we construct, and the aerial robot takes off from an elevated platform, goes inside. It's commanded several points, random points inside the house. So first it goes inside to this point, and then goes through the door inside, detects the red bucket, releases the red item inside. It then detects the blue bucket, releases the blue item inside, comes out through the window and lands on the moving platform. So let's see a video of this same experiment, where you can see over here it's entering through the door. It detected by now the red bucket, does the visual servoing, releases the red item. Then it goes through the other point where it first detects over here the blue bucket, and it goes on top and releases the blue item inside. And then it comes out through the window, and over here you can observe these are the measurements from the laser which are being affected due to the window, as well as over here when it's on top of the moving platform. And as our approach uses the flight altitude estimator presented previously, it's able to perform the mission completely autonomous and in a proper way. So during the experiment, during the competition, the real competition, we performed it in 2 trials. So the first trial was the mapping part where the aided robot first mapped the environment and it detected the buckets, it knew the location of the buckets where it was. And in the second trial, it then took off from the moving platform with the items preloaded with just a click of a button. It's going over here completely autonomous. I'm just there behind as a safety pilot. And now it enters through the door and goes into the room where the buckets are present. So over here, it goes inside the house. Over here, it finds the red bucket, releases the item inside. It finds the blue one, but it fails, although it detects it, but it doesn't drop it inside properly. Then it comes back completely autonomous and lands on the moving platform. And that's why we were so happy, because we were the only team to perform this mission completely autonomous in the IMA competition that year. So with this, we come to the part of autonomous thermal power plant inspection. For performing primary inspections of thermal power plants, the humans have to put their lives in danger in order to enter such confined spaces and also use some additional structures in order to inspect the structures or the areas of the thermal power plant. So why not perform it using an aided robot which can do it more efficiently and more faster without endangering the life of the humans either? So we present an aided robotic platform, which is the Matrix 100 platform, mounted with a Hokuya 2D laser sensor, and over here is the lightweight SF30C laser altimeter. Then it has a Zenmu C3 camera as well as an onboard illumination for capturing the details of the thermal power plant in high resolution. And then it has the DJI manifold onboard computer, which performs all the computation on board. In this case, the aerostat framework, the structure is similar to the previous IMAP competition, but I worked on integrating the new air robotic platform as well as the onboard sensors. Also, I worked on making. I also worked on making sure that these algorithms were working perfectly inside the thermal power plant, and also it had the same capabilities of mission planning. So first we perform, before going to the thermal power plant or doing any experiments, we perform the experiments in a replica, in a simulation environment, in a replica of the thermal power plant, where the aided robot is taken up from this platform and is commanded to inspect the 4 corners of the thermal power plant. And over here you can observe, if you would have used only the laser measurements, they are affected due to the cone-shaped surface of the thermal power plant. Whereas our approach, which is combining the 2D SLAM as well as the flight altitude estimator, when comparing it to the ground truth data, it's able to perform the proper inspection. So once we validated it in the simulation, we also performed several real-life experiments in our lab first, and then we went to Meirama in Galicia in order to perform the autonomous mission. So where here you can observe, this is the mission that we performed, where it was flown manually at this point of around 14 meters, and then the red trajectory is the trajectory of the aided robot that it performs autonomously for inspecting these burners of the power plant. If you observe these, the trajectory in white over here, these are the measurements in the laser which are noisy due to this cone-shaped surface of the thermal power plant. So if we wouldn't have used the flight altitude estimator in this case, the aided robot wouldn't have been able to perform this autonomous mission. So let's see a quick video of how this was performed, where you can see we had to enter through a small gap. The aided robot also had to enter into the thermal power plant through a really small gap of around 1 meter, and then it went to the point of 14 meters, and over here it's completely autonomous, inspecting the burners of the thermal power plant at high resolution, and which was validated by the inspectors over there, and they like the quality of the data that we extracted. So with this we come to the last section, which is the autonomous airplane inspection. The same case as the thermal power plant inspection. Over here for primary visual inspection, the humans have to use additional structures like this and climb high altitudes in order to inspect these, in order to just visually inspect the structures. So why not use an aided robot which is capable of doing that more efficiently. So for this approach, we use the DJI M210 aerial robotic platform, mounted it with an Oster OS1 3D laser sensor, a sonar altimeter, and for the altitude, and the bottom camera for measuring the velocities of the aerial robot. And it had a DJI Zen Muse X7 camera for capturing in high resolution the images of the airplane structure, and the DJI manifold onboard computer for performing the computation on board. Over here we changed or modified the AirStack framework in order to first integrate in the several modules for giving it the capability of autonomously inspecting the airplane. So I worked mainly on integrating the aerial robotic platform as well as the onboard sensors, and I worked on the 3D laser odometry part as well as the multi-state fusion state estimator, which was estimating the 3D pose of the aerial robot. Then it had an additional capability of obstacle sensing, because the environment was full of dynamic objects or people moving around or structures moving around. So it had the capability of stopping the mission if it detected an object in its path, and resume the mission if the object moved away. And then I worked also on the mission planning part, which read the missions given by the user in the form of text files, and it executed the points sequentially for the aerial robot to perform the inspection mission. So this is over here a real inspection mission where the aerial robot is inspecting the airplane, back projecting the point clouds. Over here the point clouds is just for demonstration, and I missed it. And over here at several altitudes, at several points, it's capturing images of the airplane. So this is one image of the airplane taken. And when it comes to the nose also, this is the image of the airplane structure it's taking. It's taking images and recording it all the time, and this is another image. So over here, in this mission, it performed the inspection of the complete front of the fuselage. So with this, we come to the conclusion of my thesis, where I'd like to mention that during the length of the entire thesis, I presented 4 state-of-the-art algorithms for increasing the capabilities of localization and mapping on board the aerial robots. So firstly, I present the flight altitude estimator using conventional sensors, which enables the aerial robot to fly in unknown and cluttered environments. Then I present the algorithm for pose estimation using semantic stereo-visual odometry, which not only combines the low-level features of the environment, but also the high-level semantic objects in order to estimate the drift-free pose of the aerial robot. Then I present an altitude estimation and planar mapping, where the aerial robot not just maps the planar surfaces path, but also estimates the flight altitude in a fuzz. And the last is the pose estimation using semantic visual SLAM, where the aerial robot creates a sparse semantic map of the environment, simultaneously estimating the pose of each pose. Then I also worked on extending the AirStack framework, integrating all the above mentioned algorithms as well as other state-of-the-art algorithms and aerial robotic platforms in order to perform several missions in challenging environments like the thermal power plant inspection, the airplane inspection, as well as other international micro-aerial vehicles competition. So for future works, I would like to ask a question. Are we ready for aggressive flights using onboard perception? I think there is still a lot of work to go. Over here you can see a very cool video where the aerial robot is capturing the ball, but over here there is a trick that the aerial robot knows the exact location of the ball. When we start using onboard perception, this can add several other, due to the aggressive flights, there can be problems. One problem, very basic, is the motion blur. So these problems cause eventually errors in the localization and mapping part also. So as future works, I would like to work on more aggressive flights of this aerial robot so that we can achieve more faster flights using these intelligent aerial robots. So during the evolution of the thesis, I've published several conference papers as well as journal papers. I've held research positions. The one which I hold currently is the one in computer vision and aerial robotics group since 5 years now, and I've also been in the Airspace Controls Lab at MIT for 2 months. And I've also worked on several industrial projects as well as international competitions and public demonstrations regarding the aerial robots. So a thesis is never incomplete without the never complete without the acknowledgements, right? First of all, I would like to thank my director, Pascual Campoy, for giving me this one opportunity to come to this lab and for do these amazing researches. My co-director, Paloma de la Puente, for advising me in all these, during all this research that I did. My family today, they weren't be able to come here, but they're watching me through this video. My second family, they're sitting there. She doesn't understand English, pero gracias a quererme y apoyarme. And the entire car department for helping me in every aspect of my thesis. And lastly, I'll not forget you guys, the entire CBAR group. I would like to give a huge round of applause for you guys. Thank you so much.
Thank you very much for the presentation.
Thank you.
Okay, so
Thank you for listening.
now we are going to start